Oh, they'll do it. Okay, perfect. Thank you. It is 9:30 and let's get started. Welcome to day two. Just a couple very quick announcements. I am proud to announce that we got our 100th follower to Instagram this morning. Lauren, stand up, wave. Thank you. You know, we weren't going to do Instagram for social media, but one of our teammates said all the young graduate students and postdocs are on social media on Instagram. So we did it, and that's one of our biggest followers. So thank you. Let's get that to 200. All right. Second thing, if you haven't, we have a couple missing talks from today. So if you haven't loaded them up, please do so as soon as possible. All right. We don't want you to get up here and not have your talk. And finally, right after I sit down, I'm going to post a new little poll that Carrie Gilbert and I developed. We're trying to get a sense of everyone's science in the room and some of the features about Roman that you're most excited about. And we're going to digest that and try to turn that into a fun interactive plot that we can show on Thursday during the panel discussion. So I encourage you to fill it out over the next day or two, and I'll post that in Slack. All right, so let's get started. Our first talk today to kick things off is the Roman Senior Project Scientist, Julie McHenry, and she will give you the mission status about the Roman Space Telescope. So Julie.
Well, thanks. So these talks get both easier and harder. Easier because I can show a single picture, and every part of Roman that's going to L2 is in that room right now. This is a picture that I took last Monday in the Goddard clean room. At the center of the room, you can see our flight solar panels. They are connected to our outer barrel assembly, and the deployable aperture cover is sort of behind the solar panels. So that's the outside bit of the observatory. The business end is in the on the right-hand side. That's what we call SCIPA. It's the spacecraft and the integrated payload assembly. The spacecraft is the hexagonal gray structure at the bottom. Immediately above that is the instrument carrier, which holds both instruments in precise optical alignment relative to the telescope, which is at the top, and the covers of the telescope here are uncovered. There's lots of people in the room. We are busy preparing SCIPA for a 3-month thermal vac test, which will be 3 months of 24/7 work and shifts for a lot of people, many of whom are in this room. OSD, the outer barrel assembly, the sun shields, and the deployable aperture cover is being prepared for acoustic testing and vibe testing. It's already been in the thermal vac chamber. SCIPA has already been through vibe testing. So we're basically coming down to the final tests of each of these large components. Then we'll put them together and be ready to launch. Launch dates. Our launch date is officially May 2027. And if you've been listening to any Roman talks, you'll realize that we are pretty consistently talking about working towards an earlier launch date. The formal agreement between the Roman project and headquarters is that we're aiming for October 2026. In practice, we are actually have enough schedule margin that if things go well, we think it's possible that we could launch as early as September 2026. And that's important because, as you heard yesterday, the president's budget request had more than a 50% cut to Roman. That doesn't mean we can't get to launch, but to get there, we would have to really realize sort of an earlier launch. It also means that we are now on track to launch earlier than the schedule that we had prior to COVID. So that meant that we had months of not being able to come into Goddard. We had months of disrupted supply chain. We had months of inefficiencies, and we've managed to catch all of that up. We are continuing to move the schedule to the left. If I had stood here before you 3 weeks ago, I would have said that SCIPA is going to leave the clean room on August 24th. It's now going to leave on August 21st, which is bad for the congressional visit on the 23rd, but it's a good story to tell. So here's some words. It's saying what I've said. We've got 100% of the flight hardware in hand. I think it's also important to emphasize that every single piece of that hardware has been through the most stringent environmental test that it will experience. So we have good reason to believe that the next steps should go smoothly because we've done most of the hard testing already. That doesn't mean that the remaining testing is unimportant. The remaining testing is critical for us to fully characterize our end-to-end performance. SCIPA, which, as I mentioned, is sort of the business end of everything. It's the actual flight telescope with the actual flight instruments and the actual flight electronics, which means that the tests that we do with SCIPA will be taking photons through the flight optics and reading them out with the flight electronics. So very, very important for end-to-end validation that we've built what we want. Another timescale of note is that we plan to ship to the Cape a year or maybe a little bit less than a year from now. So by this time next year, we will have a complete observatory, and we will be, it'll either be en route or be preparing to be en route to the Cape. We've achieved all of this while meeting or exceeding all of our science requirements. So if you've been paying attention to all of the, well, not paying attention, if you've been engaging with us to define our observation plan, our core community surveys, the performance that was assumed in those studies is the as-built performance. So we have better slew performance than we'd been assuming before. We have higher pixel operability. So we have a fantastic observatory. And let me say this again, because I can't say this too many times. We are on track for an early launch in fall 2026, but we're not late until May 2027. Okay, so this is a slide that I'm not going to talk about in any level of detail because I've got more time than I expect. Okay, we have a set of core community surveys. These represent the bulk of the observing time of the mission. This is a chart that I put together before we conducted our community process to define what these surveys are going to be. The intent is that the three pillars of Roman, astrophysics, cosmology, exoplanet demographics, are represented in the core community surveys. Cosmology and exoplanet demographics tend to drive the requirements, and the optimization is where the astrophysics is realized. And we have gone from this is broadly what we think it's going to be to a nice slide that was put together probably by Carrie, Office of Public Outreach, describing the as recommended core community surveys. I'm not going, you're going to hear more about these tomorrow. I think of note is that we have 4 deep fields. The high latitude time domain in the north and south themselves represent a deep field, and then there are deep field components in the high latitude wide area survey. So I'm not going to describe this in detail because you're going to hear about this later, but I do want to say something about what the process actually achieved. I think it was a triumph of getting broadened science input from for each survey. We heard refined examples of science cases that we'd heard before. We also heard entirely new science cases. It was taking into account the current state of scientific knowledge. All of the survey recommendations explicitly included optimizations for astrophysics. So for example, if you only cared about exoplanet demographics, you wouldn't place one of the galactic bulge time domain survey fields at the galactic center. But if you care about astrophysics, you absolutely want to look at the galactic center because there's something for many, many people right there. We also explicitly considered synergies with other facilities, and this is also extremely important. Roman and Rubin were both recommended in the same decadal survey. The hardware design of Roman has always been considered with the existence of Rubin in mind. They have been designed to be complementary right from the beginning. But to fully realize this, we also need to make sure that the surveys themselves are complementary so that we allow Roman to focus on Roman strengths and take advantage of the existence of Rubin where needed. We also considered synergies with observatories like Subaru, where we have a nice partnership with JAXA to partner with 100 nights of Subaru time. The Roman Observation Time Allocation Committee synthesized the inputs into a recommendation for an overall observing plan. But that's not the end of the story. They prioritized a strong, robust program of general astrophysics surveys, which are, let's look at other places in the sky. And right now, the Science Operations Center is working hard to optimize the implementation of this mission plan. So they are doing things like adding the capability to schedule observations at times of low background, careful consideration of the visibility of the galactic bulge fields to optimize the time spent at that highly competitive region. So there's lots of work that you haven't yet seen on making sure that we take the recommendations from the ROTAC and produce a really highly optimized set of surveys that will maximize the science return for everyone. We're currently working on how we're going to continue to get community input on the evolution of these surveys, how we can continue to engage with you, the community, as decisions about each of these surveys arise, and you'll hear more about that soon. But I want to finish with a thanks to everyone involved on the huge number of people who contributed to defining Roman's core community surveys. People contributed science ideas in pitches and white papers, and they put together presentations, and there were detailed simulations and analyses, and many people served on committees, and almost all of this work was volunteer time. And I think it's contributed not just to a great set of surveys, but also a broad understanding of the broad science that we're going to get from those surveys. So thanks all. I want to switch gears. So my talk from this point forward is incredibly boring. I've got like loads of words and very few pictures, which is of course not what I should have done at all. But here we are. We have a general investigator program. This will be a sequence of annual calls. We expect the cycle 1 to be released in November with a due date in March, which of course is where the ROSES cycle was before that. It will support analysis of any data collected by the Wide Field Instrument. So this includes the core community surveys. It includes already defined general astrophysics surveys. It includes ideas that don't really care what survey collects the data, right? You could imagine a proposal that I'm going to look at all data of a particular type, even if I don't know what the future general astrophysics surveys are going to be. It can include a science analysis of our calibration touchstone fields. So there are spots on the sky that we will frequently go back to for calibration purposes, but they're pretty cool scientifically as well. You can propose for analysis of wide field parallels during CGI observations. And what are they? Well, the CGI is going to look at one spot in the sky for a long period of time. The wide field is always on because it provides the fine guiding. So if we collect data with a wide field during a CGI observation, what we're going to have is an ultra deep field at random, known but quasi-random spots on the sky. And that is, of course, also of science interest. You can use it to support analysis of ground-based data that directly ties to Roman science. So analysis of Prime or Subaru or Roman and Rubin combined. You can propose for theoretical investigations. You can propose for new Roman general astrophysics surveys or any combination of the above. And you'll hear more about, at least I presume you'll hear more about this tomorrow. I wanted to say a few words about general astrophysics surveys because I've talked so far about the core community surveys, but general astrophysics surveys matter too. This is the remaining chunk of time that is for anything else that you might want to do with the observatory. We already have our first general astrophysics survey. The Galactic Plane Survey was selected by a committee several years ago as an example of a general astrophysics survey that would benefit by being defined early. The committee that is working on guiding the community definition of that survey is just completing its process right now. You can also propose for a general astrophysics survey in the sort of regular sort of proposal competition way. You could do this through the general investigator program 3 times during the mission in cycle 1, which is coming up this year, in cycle 3, which will be after 1 year of data is collected, and in cycle 4. And we have resources to support up to 30 new general astrophysics surveys. Our intent in the first cycle is to bias the selection so that we select fewer in the first round, because we feel that the observing resources are probably better used later in the mission when they're informed by what Roman has already seen. Okay, Roman and external synergies. This is just a sampling. It's not all of the observatories that Roman will partner with. As a survey mission, observations and data from other observatories is going to act as a multiplier for Roman science. Rubin is particularly important. Now that we've defined our surveys explicitly with the expectation of partnership with Rubin, some of our science objectives are now coupled to the availability of Rubin data. This has been taken seriously by NASA, so the NASA support of the Open Universe effort is an example of explicit support for joint Roman-Rubin cooperation. We are working with the Rubin operations leads and the agencies are talking together to help facilitate joint work with Rubin. The Subaru telescope, it provides wide optical imaging and spectroscopy. We have a partnership with JAXA where they provide 100 nights available to the Roman community as part of their contribution. The intent here isn't that JAXA, that we get 100 nights of Subaru given to Roman. The intent of this program is that it spurs cooperation and partnership between the Roman community and the Japanese Subaru community. So the emphasis is on forming collaboration and enhancing working together. We've had a white paper process here to call for science cases on how to use this, this resource. That closed in March 2025. The steering committee is currently writing the report where nobody is going to get everything that they asked for, but probably everyone who requested time is going to get something. And then finally, Euclid is our sibling in space. It's an example of a space-based optical to near IR survey telescope that is in L2. This has been enormously valuable because the Euclid team have been exceptionally generous and open in sharing their engineering lessons learned, and that has substantially impacted and improved some of our pre-launch preparations. And then the Euclid observations themselves have potential for significant science synergy with Roman. Okay, I've got 2 minutes left, and I am just going to say a couple of words about how to get involved. One way to get involved is to join the wide field working groups. These are a set of working groups that cut across science topic and provide a forum for people to work together on things of common interest. These are also extremely important to the Roman project. What we do for calibration is informed by what you, the community, discuss in the calibration group. It is the mechanism for community input into technical decisions that the Roman project takes. To join, you go to a Confluence page known as the Roman Forum. I provide the QR code there. Nobody should really need to take a snapshot of this because you all should be members already. We also think it is important for people to collaborate scientifically. So there is a Roman science collaboration that is getting going right now. It is an opportunity for people to cooperate and collaborate scientifically. You will be stronger together. It is one of the features of a survey observatory that many science cases in science skills together will maximize the return from the data. So this, collaboration is independent. The working groups report to the project. There's a reason that we've kept that separation. I have 1 minute left. That's perfect. We are currently working on plans for our first look observations. This is where Roman will debut itself to the world. We are interested in hearing from you, the community, on what you think would be good observations or targets to illustrate Roman's power. We're not arrogant enough to assume that we will have all of the good ideas. So we welcome you to, it's a super simple Google form. We're not asking for, like, you know, a vast study, or you don't have to go towards APT. You don't have to really say much at all. So if you have half an idea, please drop it in. Very welcome. And my final slide, I thought about writing an actual conclusion, and then I thought, well, this is fine. Thank you.
Okay, perfect timing. 1 second to spare. Questions?
Excellent.
All right.
Hi, Brian McDonough from Northeastern University. I was wondering, what do you think contributed to Roman being ahead of schedule?
So Roman is also cost capped. So we've had a very stringent focus on resources from the beginning. During COVID, when everything was completely haywire, we got a lot of experience of where can you spend money now to decrease schedule risk. So for example, if you think you're going to need you know, a bunch of PCB boards, you might go ahead and just buy them, because $1,000 now could save you 2 weeks down the road, and 2 weeks of Roman is worth a lot more than $1,000. So there was sort of strategic paying for things ahead of time, an enormous amount of attention to detail. Every single day, we're looking at, can we adjust the order in which we do things to save a day, or save half a day, or save an hour, and all of those little savings add up. And I also don't want to downplay the role of the team. People are working incredibly hard. I mean, we're aware that in this current fiscal environment, continuing Roman kind of requires us to stay ahead of schedule and under budget. So we're working 2 shifts, you know, start at 7 o'clock in the morning, continue to midnight, pretty much 6 days a week. And some luck, right? You know, catastrophes didn't happen, problems did. I mean, we needed to build, you know, baffles and quickly install them when we found a light leak issue in the prism and grism and filters. We've, you know, addressed a whole bunch of other little problems, but we've got pretty good at doing things quickly, making decisions quickly, optimizing the schedule continuously. I say we, I had nothing to do with it, but a really good project manager.
Any other questions? We still have 1 minute or so. Let me ask you a question. I know I don't want to put you on a spot in front of a stacked audience like this, but is there any science that you're particularly excited about to come out of Roman?
So for those of you who don't know my background, I've spent most of my career working in gamma ray transients, so high energy things that go bump in the night. And one of the things I love about studying the transient sky is that is the surprises. Some of our biggest discoveries are the things we didn't know to expect. So what excites me most about Roman is the breathtaking discovery capability, because we're not just, you know, it's not just that we have an observatory that has new capability, we're operating in a discovery mode, right? The typical mode of using Roman is to look at spots on the sky just to see what's there, not because there's a particular thing there. And I think that so I think the most exciting aspect of Roman is being prepared for the surprises and trying to figure out how to capitalize on them.
That's great. Great. Okay. Thank you very much, Julie. One more round of applause. Okay, so that was all about the mission status for a telescope that's up and coming. And now we're going to learn about a telescope and mission that has just launched, and hopefully we can learn some lessons from them, Euclid. So here's Xavier Dupac talking about science operations of the Euclid cosmology mission.
Thank you. Can you hear me? Good. Okay, so today I will talk about the Euclid science operations on behalf of two groups, the Science Operations Center, where I live near Madrid, in the ESAC, European Space Astronomy Center, the ESA establishment near Madrid, and also on behalf of the survey working group, so which consists of people in different science institutes across Europe. So you can see here part of the science collaboration of Euclid, about a third of it. It's really it's a huge community. Okay, so first of all, the Euclid mission. So I'm assuming most of you know a bit about Euclid, so I will go quickly through this. So this is what we call a medium class mission in the Cosmic Vision program of ESA. It was launched 2 years ago on 1st of July with SpaceX Falcon 9. And it provides high-resolution optical imaging and near-infrared imaging and spectroscopy. You can see here the bandpass of the visible instrument here, and there are the 3 infrared bands and the 2 infrared grisms that we call the blue and the red grisms, even though they're both in the infrared, but whatever. And okay, so yeah, so these 2 instruments make up the payload of Euclid. The goal is to reach 14,000 square degrees for the wide survey of the extragalactic sky. And you can see here also the optical path and the scheme of the telescope with the different angles we can use to depoint the telescope. The solar aspect angle here is very important. Also the alpha angle or the roll angle that allows us to point the telescope away from the main axis. Okay, and the goal is to get accurate weak lensing and galaxy clustering measurements, and also a wide range of additional sciences. So some of the technological challenges here were the following. So I think it's the biggest infrared focal plane flown in space so far. The pointing accuracy and stability needs to be very good. Also, we need fast repointing capabilities, and we need exquisite image quality, performance, stability, and all of it from L2. So we also have the challenge of a really big data volume transmission from L2. For ESA, it's really the biggest challenge in this respect ever in terms of volume of data. So the Euclid science, I'll go very quickly on this. You all know this very well. So Euclid is going to observe the last 10 billion years of cosmic history. So basically from the cosmic noon, peak of star and galaxy formation, and that's also roughly at the time where the dark energy starts to dominate, and so the expansion starts to accelerate. And so to do that, we want to observe a lot of galaxies. And we have 2 main probes for cosmology. That is this weak lensing. So there will be later on today a talk by Hank on this. So just to mention that, well, what you all know, that weak lensing is we need to observe the shapes of about 1 billion galaxies, 1.5 billion galaxies. And that by measuring the shapes, we want to infer the cosmic shear. That is the way the clumps of dark matter and the line of sight modify the shapes of all the galaxies via gravitational lensing. And so in order to reconstruct the map of mass in the universe. And the other most important probe for Euclid is the baryonic acoustic oscillations. So this is these bubbles formed by sound waves in the primordial plasma. So it's visible in the CMB. This scale is visible as a big first peak in the CMB. And this is something you can see at other later epochs. Of course, in the universe, you see galaxies gathering preferentially or forming preferentially on those scales, as you can see here. So this provides us a standard ruler for then constraining cosmology. Okay, going to Euclid operations, so how it is organized. So we have here the spacecraft. It communicates to Earth through ground station network. We have ESA, and the data then go to the Mission Operations Center that is in Darmstadt in Germany. And what they do is they command the spacecraft, they get the telemetry from the ground station, and they ensure the health and safety of the spacecraft. From there, it goes to different places. Well, it goes to Earth in Madrid, to the Science Operations Center. The Science Operations Center is basically doing a number of things. So planning from what we get from the community, from the Euclid Consortium, it's called the Survey Operations Support Team. It also monitors survey evolution. It provides a quick look analysis. Also makes the first level of the data processing, called the level 1. And it provides the science archive and maintains the operational archive. Then we have also the instrument team here that's in charge of instrument operations and monitoring and provides calibration requests and support to the processing. We have the SOS, so the survey operations support team that designs and produces the survey. And then we have all the data processing system here with the different science data centers in different countries. And each of these data centers is assigned different functions that are called OUs, or organizational units. And they do different parts of the processing. So for example, here you have the photometric redshift, the shear, the VIS the processing, the level 3 processing, the spectroscopy, etc. And main catalog, that is the mirror catalog. Okay, so you see that some of the SDCs have many different tasks. Others are more specialized in one of the tasks. But this is quite complex organization to manage. But yeah, this is how it is done in Europe. So. I never said that, sorry. Moving to the survey design, the region of interest. So what we do, for the primary cosmology objectives, we need to observe about 1.5 billion galaxies for weak lensing and 35 million redshift for the galaxy clustering. And because of that, we need about 40,000 square degrees of the extragalactic sky with low ZODI background and low galactic extinction. And that, with Euclid, it needs 6 years for doing that. So the region of interest we define is the maximum area on which we can have the observations compliant with the science requirements. So this is what you can see here on this, all that's inside the blue contours. So you have 4 areas. This is our region of interest. So we avoid basically the galactic plane and the ecliptic plane where the ZODI light is. So when we schedule the wide survey, we observe as much of the region of interest as possible. And we also need 3 deep fields for calibration with a gain in depth of about 2 magnitudes compared to the wide. And we also have some auxiliary fields for some specific calibrations. And also the so-called self-calibration is done in the ecliptic North Pole, because this is an area that is always visible with Euclid. Since we are L2, we have this symmetry around the ecliptic. So, okay, there will be a talk about this later this morning by Ismael Terreno, so I'm not going to describe this scheduling of the survey, but this is going to be covered by Ismael. And this is basically the coverage prediction at the end of the nominal mission. So you can see, well, basically 2 big areas in the north and in the south, and you have this, what we call these islands in the south here, that is still part of the region of interest. And the coloring gives you the time where we are observing these areas. So the first region, the ones we have already observed the first year, they are in purple and deep blue, and then go to green. This will be for the 3rd year, 4th year, and at the end we observe areas that are yellow, red here, and that are also not so good in terms of galactic dust, reddening, and or ZODI, but the best areas are observed in the first years of the mission, in principle. Okay, the replanning concept and survey operations. So basically, the constraints coming from the spacecraft and celestial constraints are compiled at ESA and taken by the source to produce what we call a reference survey definition. And the reference survey definition contains the wide, the deep, and the calibration, so everything for the full nominal missions, 5 years and 10 months, starting on February 14, 2024. What we do at SOC is validate the RSD and processes it for operational use, and then generate the pointing requests to the MOC. And then when we need to replan, we have different ways. So the fastest way is through what we call the local replanning. So this happens typically when there is one-off change that needs to be performed quickly, sacrificing temporarily a few observations to include something else like a calibration or something. And for the more complex changes, it requires what we call a strategic replanning. So in this case, the source is involved, and this typically occurs two or three times a year. So far, it was the case. Okay, now coming to the operational reality, which turned out, I mean, we all want operations to be like a flowing river, very quiet, but it turned out to be a song of ice and fire. I'm sure some of you are familiar with this. So first thing, ice contamination. So you can see here what happened. So this is basically the sensitivity of the vis detectors. So at the beginning it was okay, and it started to degrade. We understood that it was because of ice, probably. So we did here the first decontamination campaign where we heated part of the telescope, and bop, went up, was very good, but immediately started to degrade even quicker than before. So then we realized something was wrong, so we had to do a second decontamination. We did it a bit differently, but this time it worked. It's very good since then. We don't really understand why, but apparently it worked. So some magic. Okay, so this period, this 2.5 months, we have to reobserve because they are not good enough for the main cosmology. Another problem was the stray light from the sun that came through some path that we didn't think it could occur, but it did. And that was really something that forced us to completely redesign the survey, because as you can see here, the stray light was very strong when we used the roll angle, so in the positive side, or in the middle, that was the default observing mode. But now we have to observe there. We have to observe where the stray light is not there. And well, we were lucky at least that some valid range of this roll angle was still okay. So we had to redesign the survey to use only these negative values. But in the process, we're also losing survey efficiency. So we have more overlap of the tiles. So that means that we are covering less area over the same amount of time. Okay, so that was the two big problems. The other ones were not so big, but also a bit problematic. Some X-ray flares that affect part of the detectors. Sometimes we have proton showers due to the sun activity, but this is once in a while. And we had also some fine guidance sensor performance issues that impacted the data periodically. Now this is largely solved by the software improvement that were made. Okay, so just mentioning that because of this, the survey area will not reach 14,000 at the end of the nominal mission, but we aim to reach 12,800, something like that. So we'll be short by about 1,000. There will be some periods of unallocated time because at some point we run out of areas in some of the ecliptic longitudes in the region of interest. So those areas, if we don't use them to replan things that didn't work well before, they will be used for some other programs. So they will be filled by some dedicated program. Okay, just finally, the public releases. So you've been seeing already the early release observations, 17 fields. We had the Q1 release, so that was one pass of the deep fields earlier this year in March. You can see here where the deep fields are in yellow and the 17 early release observations in white. So the first cosmology release called DR1 is coming. So it's coming October 26th. So it will be 1 year of data, 1900 square degrees. The DR2 is coming in 2028 in principle with 3 years data, and finally the DR3 6 years data by 2031. And this is just a few nice images that you may have seen already from Euclid. Okay, last slide. The building of the Euclid survey is very complex in the first place, with numerous operational and scientific constraints, resulting in a very constrained realization of the survey. The PV phase was also extended to accommodate the phase diversity campaign that resulted in the loss of 2 months for the nominal mission. And as I mentioned, there were additional problems like stray light and the ice that made it more difficult, but okay. So we are a bit late, let's say, in gathering data compared to the early plans, but okay, it's going well anyway. The public release is coming in October, and yes, so the Euclid survey is progressing very well despite some adverse conditions so far. Thank you for your attention.
Any questions?
Were there any synergies with ground-based observatories that influence the Euclid survey strategy, or more generally in particular, are there any synergies that collaborators are excited about?
Yeah, so I think this is something that Ishmael will touch on, but yes, indeed, we have the need of ground-based coverage for the photometric redshift in the optical, because we have only one wide visible band, and so we need also the visible bands from the ground, and so this influences us in the sense also that the survey of Euclid has to be somehow coordinated so that for the data release we don't end up having observed areas where we don't already have the ground-based coverage. So this is how we try to coordinate those so that we get the ground-based data before or at the same time we get the space data basically. So.
I saw your hand and then we'll call. Yep.
What are the prospects for the mission extension at the end? Are there any technical limitations, or is it just a question of politics?
So there are several questions. So one is if we get the money, so we have to propose an extension. So normally at ESA, the extensions of missions is 2 years. So typically you start asking for the extension a couple of years before the end. You get a 2-year extension, or you don't get it. And then after that, you get another one. I mean, if it works, it would be normal that we get an extension. Okay, so on the technical side, in terms of like consumables on board, it should be okay. As far as we can see, we should be going for maybe another 3-4 years after the nominal mission. That shouldn't be a problem as far as we can see now. Now another question is how the detectors degrade. That for the moment we'll see. It's not clear, but if it's okay, then we should be able to get an extension.
Very last question.
Yeah, so it sounds like the stray light came as a surprise. Once you know it exists, can you like go back and work out where it came from?
Yes. So it was actually found out where it came from. So it was a funny path that the sun rays hit one of the thrusters that's like jutting out of the spacecraft, and it reflects onto the cavity. Somehow it enters with funny angles into the cavity where the instruments are. So it was a design issue, but yeah, it was not seen before. So.
Okay, well, thank you very much. I know there was an online question. We're just running behind schedule, so we're out of time. If you want to continue the conversation, there's coffee. Also, I encourage people to converse on Slack too. That's a great chance to follow up some questions. All right, thank you.